Hello, I'm Dr. Michael Gordon, Principal Research Scientist at Arno Labs. Today we'll present an overview and demo of our CodeHawk analysis and patching platform. CodeHawk enables organizations to fix bugs or vulnerabilities in legacy code with high assurance, without source code or access to the original developer. CodeHawk has been developed over multiple DARPA and IARPA grants, with CodeHawk's binary modification capabilities originating under DARPA's AMP program and advancing under ARPA-H's DigiHeals program. Organizations depend on long-service legacy systems. Subs, warplanes, embedded systems often operate for decades, with thousands of hardware and software components. These systems require updates to address bugs and vulnerabilities, update capabilities, yet vendor support is typically limited. Many vendors disappear long before the systems retire. CodeHawk changes the economics of modifying legacy systems by reducing the cost and increasing the assurance of patching binaries, without requiring reverse engineering or source code. We enable a developer to modify a binary with workflows similar to how they develop with source code. A developer does not need to reason about the underlying binary. Then CodeHawk automatically applies the new logic to the underlying binary without recompilation and with minimal binary changes. We employ formal methods to ensure that modifications are implemented correctly and fix vulnerabilities without unintended side effects. Assurance results support trust, maintaining testing, and certification. All this enables rapid deployment of critical updates to legacy systems. In today's demo, we will develop a high-assurance binary patch for a real vulnerability in a commercial medical device firmware and prove the patch is correct. We demonstrate our developer-friendly workflow that expresses binary modifications in plain C code with validated translations at every step. We show the results of our verifications and analyses that prove the patch fixes the vulnerability without changing any correct behaviors. And hopefully with our demo, you'll appreciate how CodeHawk revolutionizes the modification of legacy binaries. Thank you, and now over to Ricardo, who will guide you through the demo.
The user interface of our tool is built as a plugin for Binary Ninja, a popular binary analysis platform from the folks at Vector35. Here we have the vulnerable binary already open and at the function with the bug. This function called parses data from 5001. To begin the patching process, we select the CodeHawk Patcher view from the drop-down menu. This asks CodeHawk to analyze the function in preparation for patching. Analyzing this function takes about 4 minutes, but for the purposes of this demo, we already have the analysis results catch. So as I mentioned, this submits the binary and the function for analysis by CodeHawk. The CodeHawk Binary Analyzer is our open source static binary analyzer. It is built around an abstract interpretation engine, which is also open source. It generates invariants or facts about program execution at every program point, and it uses those to generate a high-level trusted C-level lifting specifically built for binary patching. Here we can see the lifting that CodeHawk generated for the function that we're interested in patching. As you can see, it contains types. Here's, for example, for this function parameter, global variables, as you can see in the sidebar, information about external functions called by the target function, and high-level control flow constructs such as switch statements, function calls, external function calls with return values, and so on. This lifting is a true representation of the semantics of the underlying binary. It is built on top of a tower of IRs, which preserve full provenance information from the visible high-level lifting constructs that we're showing to the developer, down to the corresponding individual instructions at the binary. This tower of IRs is our secret sauce that enables the generation of minimally invasive binary patches with full assurances as to their correctness. The bug we're going to patch is a buffer overflow at these two particular lines. As you can see, a field in the structure that's being passed as an argument to this function is being used as an index into this array. And if we look at the sidebar under the global variables, we can see that GDataArray is an array of 64 entries, or this particular type. One of the most important aspects of our tool is that it allows you to analyze the lifting looking for potential memory safety issues. Under the hood, this uses the CodeHawk C Analyzer, an open source static C analyzer, which has a model of C semantics, and it uses that model to identify instances of undefined behavior. It then generates proof obligations corresponding to each of those instances, and then tries to prove or discharge those obligations given the program context. Any proofs that are left open are flagged as they represent potential sources of trouble. As you can see, a small number of issues have been flagged, but interestingly enough, the particular lines with the bug are not. Instead, they're being marked as having preconditions. What this means is that if callers to this function perform the checks displayed in the precondition, then this code is safe. Otherwise, it isn't. So let's go ahead and see if that's the case. Our tool gives you the ability to analyze more than one function so that you can get a full picture as you develop a patch. Since we're interested in verifying the preconditions to the lines with the bug, let's go ahead and analyze the callers to the function we're interested in. In this case, there is only one function that we need to worry about. So let's add it into the analysis. As you can see here, it's our original function. Then if we scroll down, here's the caller. And then let's run the lifting analysis once again. Here are the preconditions that we're interested in. Then we're going to scroll all the way to the bottom to the place where the caller actually makes the call to parses data. As we can see, those preconditions have not met, and now those issues have been flagged. In particular, we can see that the upper bound, there's no checks for the upper bound on the token 1 member of the structure. And even worse, we can see that the value can go basically unbounded, which can translate to access to full memory. So let's look on the left and try to understand what the listening function is doing. So you can see here, it's basically an infinite loop that is reading data from the network and performing some very simple parsing. And if we focus on these lines, we can see that what this is doing is looking for the delimiter, in this particular the semicolon, converting that blindly to an integer and then assign it to the value, to the field that, if we scroll up, is the one that's being used as an index into the array. So this code is doing no checks on completely untrusted network input. And with this information, we can now develop a patch. In this case, we actually have a couple of locations where we can insert the checks required to get rid of the buffer overflow. We could do it right as here as the data is being read from the network, or we could do it up here just before the values are being used to index into the array. And this is what's great about our approach. It allows you to reason in very high-level terms about the best mitigation without having to be bogged down by the details of implementing the binary patch. For this demonstration, we're going to do the patch right here as the data is being read from the network. And the way you develop a patch is you type C code. You can reference local variables, you can reference global variables, you can make function calls, you can use complex control flow constructs like continue, like compounding statements. So I just asked the C analyzer to check again if the patch now solves the issues that it had raised before. And while we wait for that, we can talk about what the patch is doing, which is basically checking that the value we read from the network is within the bounds of the array. So now if we scroll down to the call to parses data, we can see that every single issue related to the token 1 field is now gone. We can now generate the binary patch. To do that, we click on this button. Under the hood, the system figures out what parts of the lifting have changed and converts those changes into specific binary instructions that it can surgically insert at the binary level. So to be clear, we are not recompiling the whole function with the changes to the lifting that was made. As well, we get this dialog telling us that we now have a patch binary and details on how that patch binary was implemented. In this case, a trampoline was used, and a trampoline is required because we inserted new code. If we don't use a trampoline, we would need to move code around. We would have wide-ranging repercussions across the binary. If we're satisfied with this, we can then submit the patch binary for analysis. And what this will do is perform a relational analysis between the original and the patch binary, validate that the patch was actually implemented correctly, and then generate a number of assurances that will help us evaluate whether the final patch binary addresses the issues that we set to resolve. Once the relational analysis is finished, the user interface switches into assurance mode. In this mode, the system shows you proof that the patch was correctly implemented and that it fixes the vulnerability without any unintended consequences. First off, we are given a summary of the changes to the binary. The idea with this view is that you can see that the only parts that change in the whole binary are the ones that were supposed to change. So as we can see here, the original binary had 3,260 functions, and the patch binary has the exact same number, and out of those, only one changed. And under here, we can see the detail of those change. And so as we expected, the function that we patch has changed. And then in addition, the trampoline location also it's marked as change in the patch binary. The system under the hood is able to automatically find free space to put the trampoline, and then it tells you here where that went. Next up is the high-level lifting analysis. In this view, we show you the results of running the CodeHawk C analyzer on the original lifting and on the patch lifting. The idea here is to show you at a high level that the patch actually fixes the underlying buffer overflow. So on the left-hand side, you can see the issues that the CodeHawk C analyzer raised that were underlying the buffer overflow, and on the right, those are gone. So right away, you have proof that the patch binary does not have the vulnerability. And the key here is that CodeHawk, as part of its relational analysis and lifting generation, is able to validate the trampoline and then inline the code that was part of the trampoline as part of the lifted function. So now with the checks that we implemented in place, the CodeHawk C analyzer can verify that the bug has been fixed. Moving on, we go into the binary lifting comparison view. This assurance view shows you a textual comparison between the lifting for the original binary and the lifting for the patch binary. As you can see, nothing in the parse data function changed as expected, and in the listening function, the only part that changed is the code that we added. This is key proof that we did minimal modification to the binary and that the insertion of the code that implements the patch was very surgical. Looking towards expensive recertification efforts, this is huge because it allows you to focus all your efforts on the small modification that we did to the binary while being assured that nothing else in the binary has changed. The final assurance view that we're going to see in this demo is the user lifting comparison. In this view, we do a textual comparison between the lifting that you submitted to the system as part of the patch development and the lifting that we got out of the patch binary. And the idea here is that the developer can verify that the logic underlying the changes that they made to the lifting are represented in the binary. In this case, you can see that the conditionals are equivalently the same, even though the text is different. And so interestingly enough, we can see that while we developed the patch using the structure fields, under the hood, the system realized that those values were being stored in a register from the return value of A to I, and reuse those, allowing it to do a very minimal patch implementation. So these are the kinds of details that binary patching requires and that our system takes care of so that the developer can focus on all the high-level details instead of being bogged down by the minutiae of the binary modification. And once you're done, all you have to do is save the patch binary and then move on to the rest of the recertification and dynamic testing processes. Thank you so much.
Arno Labs offers CodeHawk as a tool for download, and we can train your developers to use it. You can also engage Arno Labs to fix the issues in your legacy systems. We use CodeHawk internally to understand the problem, fix it, and provide assurance. So please reach out to us if you want to learn more.